Welcome everyone to this second e-Safe Academy webinar entitled Envelope Solution for Seismic and Energy Renovation. I am Veronica Christofidis from Overim, and we are leading the dissemination and communication activities within the e-Safe project. This event is the second of a series of 3 webinars called e-Safe Academy. That is an engaging platform that we designed to share insights, foster dialogue, and explore innovative solutions in the field of building renovation. And if you missed the first appointment, you will be able to find it very soon on our YouTube channel. What is e-Safe? e-Safe is an H2020 project aiming to contribute to the deep renovation of EU building stock by developing an innovative market-ready system that combines decarbonization with earthquake resilience. What makes e-Safe unique? It is its approach. It doesn't focus just on structural and environmental improvement, but also keeps in mind indoor comfort, quicker and more cost-effective implementation, affordable financing option, and minimal disruption for the occupants. The effectiveness of this system is currently being tested in 3 pilot buildings situated in Italy and Romania. And our focus today will be on exploring innovative and sustainable solutions that make retrofitting projects more affordable, accessible, and impactful. And to do this, we will have with us our partner from University of Catania, the e-Safe coordinator, University of Bologna, and the Norwegian University of Life Sciences. They will introduce to us the e-Safe integrated renovation solutions, specifically the e-TIL and e-panel and e-EXOS and e-panel technologies. And they will delve into experimental testing, the structural application of the technologies in Catania pilot building, and the innovative system application in virtual pilot. Joining us today, there are Carola Tardo, Research Fellow of Building Design at the University of Catania, Francesca Barbagallo, Assistant Professor of Structural Design at University of Catania, Claudio Mazzotti, Professor of Construction Technology at University of Bologna, and Roberto Tomasi, Professor of Timber Engineering at the Norwegian University of Life Sciences. So, before I pass the floor to our speakers, I would like to encourage all the participants to submit their question through Slido. You can see the QR code. You will see the QR code displayed on the screen, and if not, you will find a link in the chat. So we will have a Q&A session at the end, and please submit your question. Now I will leave the floor to Carola, and please enjoy the webinar. Thank you.
Hi, everyone. I'm Carola Tardo, and I'm a researcher of architectural engineering from the Department of Civil Engineering and Architecture of the University of Catania. Today, me and my colleagues will illustrate to you the main outcomes of a research project that was aimed at developing and demonstrating novel technical solutions for both seismic and energy renovation of modern building stock. Before that, I will give you a brief introduction about this project. How did the e-Safe project start? This project was conceived from the evidence of the current conditions of the existing buildings. At current state, in the European seismic countries, such as Italy, Turkey, Romania, and the countries of the whole Balkan Peninsula, most of the building stock is not only highly energy intensive, but also highly earthquake prone. And this because it was built before the enforcement of the most recent and effective energy and seismic codes. The data on the environmental impact of buildings are still well known. Buildings are responsible for 14% of the final energy demand and for approximately 36% of greenhouse gas emissions. Less known, instead, are the data on the consequences of earthquakes. Only in the last 50 years, for instance, in Europe, earthquakes caused more of 36,000 deaths, around 1.3 million homeless, and over 220 billion monetary losses. These data show that in these countries there is a strong need of renovation actions that synergically integrate both energy efficient and anti-seismic interventions. However, today the implementation of retrofit strategies which combine seismic and energy issues is mainly limited by the excessive cost and the high level of invasiveness of the most common seismic retrofit techniques. These techniques indeed often require a long time for implementation, the relocation of the occupants during works, and major demolition and reconstruction works. To mitigate these barriers, the aim of the e-SAFE project was thus developing novel and innovative integrated retrofit technologies which are able also to reduce cost and time for implementation, reduce disturbance to the users, and also reduce the environmental impact of the intervention. To this intent, this project was carried out by a multidisciplinary consortium which involved 12 partners from 8 different European countries. So, what retrofit solution did we develop? We developed 2 retrofit solutions for buildings having reinforced concrete frame structure. The solutions specifically involve the use of prefabricated technologies to be applied from the outside of the building. As you can see in this slide, one of these solutions consists of cladding the external envelope of the building with prefabricated wooden panels. 2 types of panels are combined, which are called e-CLT and e-panel technologies. The e-CLT technology consists of structural and insulating panels, which are applied to the outer blind wall of the building. These panels are basically made of cross-laminated timber and are fixed to the existing structure by means of steel connections which act as energy dissipation devices. Specifically, we have designed novel and innovative friction dampers. Next speakers will talk you more in detail about the design and the development of these friction dampers. In case of earthquake, the aim of the e-CLT panels is thus exploiting the high mechanical properties of CLT and the additional energy dissipation in order to increase both the seismic and dissipative capacity of the existing structure in order to reduce the drift demand of the structure and thus its damage. The e-CLT were conceived to be combined with the e-panels technologies that instead consist of only insulating panels with a lighter timber frame. These panels are applied to the windowy walls of the building and can integrate new high-performing windows in replacement of the existing ones. If the e-CLT technology is not applicable or is not sufficient to achieve proper levels of seismic improvement, a second retrofit solution consists of cladding the external envelope of the building with only insulating panels and combining them with structural 3D steel trusses. In case of earthquake, the aim of this steel trusses is forcing a uniform distribution of the story drift along the height of the building to avoid the formation of the mechanism of soft story collapse and also to reduce the drift demand of the structure. So I have briefly described the e-safe envelope technologies. Next speakers will show you the main research activities that were carried out to develop these technologies. So now I give the floor to Professor Tomasi, who will talk you about the e-CLT technology and especially focusing on the design and the experimental activities of the friction dampers. So I give the floor to Professor Tomasi. Thank you.
Thank you, Carola. Can you see my presentation?
Yes, we can.
Okay, thank you.
It's in
Yes,
the wrong screen. You should swap the screen.
Okay, now you should see my presentation. Is this correct?
Yeah, if you change the display settings, if you click at the top left, display settings. Display settings at the top of your screen, top left.
Display
click
setting,
there,
okay.
there.
Swap.
Duplicate or swap? Yeah.
Okay, now it's good?
Good.
Okay. Yes, I'm Roberto Tomasi from Norwegian University of Life Science. I'm going to present briefly what we have done in e-safe. Okay, Carola has already described the consortium. It's pretty big. And the idea that is here in a nutshell that we can cover with cladding panels the existing LC frame buildings, where the connection system is the core of the idea. And this work is involves three main units: Uni Catania, Uni Bologna, and Norwegian University of Life Science at different scale. At the beginning, we started with a connection system with a scale of the connection. And then in Bologna, he has done a scale of the frame. And then in Catania, there's been a pilot case. And also on top of that, we have a spin-off currently at Lisbon in the shaking table test, where we have performed some tests on the system. But you understand that the core is the connection system. So in collaboration with the other units, we are started to develop this system from an initial idea, which was, of course, have some need to improve at the beginning. And the idea was to have this curve steel plates that connect the panel to the RC frame and connect it to the other panel by means of friction-based connection. We call it this first concept standard 2H because there were two holes in the system. But then you can see that we develop several geometries because we investigate some improvement of the system, and basically we can individuate three phases of testing the connection. That also was depending on the circumstances of the test, because that was also in COVID time. So we have some difficulties, and we have to change also the testing machine 3 times. So we have a 3 testing machine involved. One they were all universal testing machine, but we started with a small one, 100 kilonewton, and at the end we were able to use the biggest one, 1200 kilonewton Roll machine. In the first phase, we have 4 geometry under investigation. The first idea, where we have 2 holes, then we try to reduce the number of holes to 1, and we want also to reduce the number of bend curve in the system. So we introduced this alternative connection, where also this alternative connection, we could also reduce the eccentricity, the internal eccentricity of the connection. And all these things were favorable in the global behavior of the system, because we could reduce the number of bends, so have a better behavior. And also important things was also to introduce a so-called cap plate here, and a couple of shim layers that were specifically chosen in terms of material to improve the friction behavior. And in this campaign, we changed a lot of materials. We changed also the geometry, of course, but also the different preload of the bolts. So we could have different level of friction on the system. And also the testing setup was made in order to isolate the force on the friction-based system. And these are the results in terms of diagram, hysteresis diagrams. And from the beginning was clear that the system could work after this. We have introduced this system, and that we have a friction experimentally under between 0.1 and 0.3. So on average, we have 0.2 that was pretty consistent with literature for this material. The introduction of the alternative geometry show us improvement in the results, and also in a more stable friction behavior. Then in the other 2 phases, we end up to investigate another solution that was similar to this one. We call it hybrid because we reverse one of the plates. But at the end, that was not the solution investigated or chosen for final configuration. But what was important also the possibility to investigate also the presence of CLT panel, not just isolating the friction damper, but also to study the CLT panel. And that was this type of test we have done in this configuration, where we could understand also that there is some role of for example, the connection between the steel plates and the CLT panels that can also influence the global behavior of the system. These are some results in terms of friction dampers. And here, okay, we have a summary of the result, where we have the possibility to isolate the behavior of the connection, and also to investigate also the influence of the CLT plates. And you can see that the green diagram show that there was also some rotation that cannot be neglected completely. But the system seems also to work and to function. And at the end, okay, this is a summary of the concept that we of course we were aiming to ideal friction behavior, and then we prove the system with a steel setup and CLT setup, and we achieve a behavior that is not ideal. Of course, it's not equivalent to the ideal, but is pretty close to that behavior. And at the end, there was also some consideration, like technological consideration, that end up with a chosen solution. That is, I come back to previous slide, that the final solution is the red one, this one under red square, which probably the next speaker will talk a little bit more, because this solution has also some intermediate elements in order to facilitate the mounting process of the system in the real building. Okay. At the end, we have some publication that summarize all these results, and then I think I'm finished. I can leave the stage to the next speaker.
Okay, thank you, Roberto. Now you should see the screen, isn't it?
Yes.
Yeah, correctly. So, good afternoon, all. My name is Claudio Mazzotti. I'm a professor at the University of Bologna, and I would like to keep moving from the previous point, previous activities explained by Professor Tomasi, to move on a larger scale. What we did here in Bologna was to test the dampers previously developed, but this time not as a single element, but included in the whole system in a lab scale, of course. So we developed a mock-up, an experimental mock-up, where we started from a reinforced concrete frame infilled with unreinforced masonry. This is the elementary cell of what we do have in mind, a reinforced concrete frame, a multi-story, multi-span building, okay? And then we add to the conventional technology, we add the CLT panel properly connected through the friction dampers that have been already explained. And this is the final system properly assembled. So we can see on the back the RC frame. We cannot see the masonry infill behind, which is behind the CLT panel. And then we have at the top two rigid fixing points, and the dampers were positioned at the bottom in order to be able to transmit the shear force while dissipating energy. This mock-up, this system has been tested under axial compression in terms of columns and horizontal shear force applied to the beam, having in mind the earthquake force, the horizontal force produced by an earthquake. So we developed some cyclic tests on this type of system. Here you can see some pictures of the process, of the construction process. The RC frame in particular was designed together with the colleagues from University of Catania by following non-seismic standard, which is the typical approach of old buildings made in the 50s, in the 60s, in the 70s. So few stirrups, strong beam, weak column philosophy, etc., etc. And then here you can see the installation of the wall, of the masonry wall, again by using typical materials of that age, 50s, 60s, etc. And then we also apply the wooden panel, and we place a number of instruments. I don't have the time to properly comment on them, but we were able to observe and measure all the main parameters governing the cinematic behavior of the system. And this is the history we applied in terms of horizontal force to the frame. So cyclic forces of increasing, we control the displacement, the top displacement with respect to the bottom one. So we increase the amplitude of the displacement. After some preliminary tests, we understood that the damper previously developed, when used in real scale application, when introduced inside a structural behavior, has some limitation that should have been improved and modified. So from the, let's say, the original version tested only at the laboratory scale as a single element, we moved to a new one, improved in terms of all the limitation we observed during those preliminary tests. In particular, as you can see here in this picture, when using the full-scale system, we observed that the CLT panel developed some rocking behavior. That was one of the most important observations, and this is unavoidable. Okay, so correspondingly, the dampers here at the bottom were subjected not only to horizontal forces, but also in the original version to important vertical forces. And the drawback of this application of vertical forces was that the preload produced to apply to the bolts in order to create friction was strongly reduced. Okay, so we developed a new scheme where we divided the system, we decoupled the system connected to the CLT panel from the real damper itself and what is following below. Okay, through this box is free to vertically move inside this further C-shaped profile. And the box at the same time is linked through the friction surfaces to the bottom beam or the CLT panel below. In this way, we were able to avoid the vertical application of forces directly to the damper. We develop other, let's say, further modifications, but in my mind, they are secondary modifications, since the main one is the one I've just described. And we optimize also the way in which the friction was developed, the materials, and something more. These are some more details and all the aspects which were improved. Another important thing was to create a uniform surface which have to remain plain even during the test. So we increased the number of bolts and the thickness of these plates over here, pushing the shim layer against the moving steel plate. Then we repeated the test now with the final configuration of the damper, and these are some of the most important results, but a small amount of those available. And the black line is the curve coming from the strengthened frame with the CLT panels and the e-damper, while the red curve is the one from an original frame, exactly with the same characteristic and infills, but without the reinforcement. As you can see, we can observe some important difference, which were the purpose of this technology, of the introduction of this technology. First of all, at the beginning, we observed an increase in terms of stiffness due to the application of the CLT panel and the dampers with respect to small interstory drift. At the peak, we registered the failure of the meson rib infill, and then the force went down following a sort of plateau where the RC frame and the e-CLT system started working together. Okay, in terms of forces, the difference is not so large, but the tremendously large difference is in terms of dissipated energy. You can see that by pushing forward the interstory drift, the red curve becomes thinner, the red cycles become thinner and thinner, okay, which means you are able to dissipate less and less energy. On the other side, by developing the same interstory drift with the strengthened system, you can see that the area enclosed by the black circles is much larger, which means the system will be able to dissipate a tremendously larger amount of energy. And this is of paramount importance when dealing with seismic behavior. At the same time, the system was able to reach target displacement of more than 10 relative displacement of more than 10 centimeters, which was another target parameter that we were able to obtain. This is a really short video of the test, so you can see the frame, the e-CLT panel, and the dampers here below, and the cyclic test. These vertical ties are those necessary for the application of axial force. So you can see how large the displacement were, and nonetheless the system was able to work, leaving the e-CLT panel completely undamaged. And this is another safety measure against the overturning of the infill walls, introducing a larger safety in the behavior of the system. If we remember some past earthquake, we got lots of damages exactly due to overturning the out-of-plane failure of walls. In this case, those out-of-plane failures are avoided. In specific terms of shape of the cycles, of the dissipation cycles, measurable from the e-dampers, this is an example. So again, they are still similar to what we saw before after the laboratory test, only the square shape is still quite large, meaning that the system, even when subjected to very large relative displacement, is able to dissipate really large amount of energy. This is a close view of the system, and this is again a quick video of the cycles. The important thing here is to observe the box with respect to the other plate. When reversing the cycles, you can see that the upper plate changed the vertical position with respect to the box. And in this case, actually, we have no consequences since the two are disconnected, okay? Only the vertical walls are in contact, transmitting necessarily the shear forces. Okay, as for the failure modes, the introduction of the strengthening system I've just presented introduced some differences. Usually we are used to observe failure of the infills through the development of diagonal cracks. This is the case. This is at failure, so you can see the shape of what is remaining. On the other side, when introducing the CLT panel, the orientation of the cracks changes, and we have a sort of K shape, okay, following the point of fixing the CLT panels to the reinforced concrete frame. So we observe really interesting things. Previously, I show you the behavior of the system on the other side of this frame. So even if the CLT panel is completely undamaged, the infills behind is completely broken. At failure, we completely exploited, even in the reinforced case, we completely exploited the plastic capability of the plastic hinges, which were developed as expected at the top and at the bottom of the columns, since they were weaker than the beam, as in the 60s and 70s happened. And so we observed buckling of compressed bar, complete detachment of concrete under compression, etc., which are the typical damages of reinforced concrete frame under major earthquake. But nonetheless, the system was still able to sustain a number of these tests. I don't have the time to show you all the results, but even after reaching this level of damage, we restored partially the frame and developed other tests, and the performances were still good, really good. In terms, and then I'm closing, in terms of dissipated energy, you can see the red curve as the amount of energy dissipated cycle after cycle by the conventional reinforced concrete frame, while the black curve is the one coming from the strengthened one. As you can see at the beginning, for a really small drift, the difference between the two systems is negligible, which means that at the beginning, the dissipation system is not activating, not immediately at least. But then when you increase the drift more than 0.5%, the two curves start behaving completely different. And in the end, in front of major earthquake where large drifts are required, you can see that you have twice, 3, 4 times more dissipated energy than in the conventional case. So this was the proof of the effectiveness and the success of the application of this technology. Okay, that's it. Thank you for your attention. And now I leave the floor to Carola for moving forward with the presentation. Thank you again.
Thank you, Professor Mazzotti. I share again my screen. Okay, so hi everyone again. Now I will talk about the main technological issues regarding the design of the e-safe technologies, so the e-CLT and e-panel, and their application to the pilot buildings. As regard the e-CLT and e-panel technologies, this panel were designed to be totally prefabricated off-site and to ensure high performance in terms of mechanical and thermal resistance, safety in case of fire, water tightness and height tightness, and also impact resistance. Each panel was specifically provided of a stratigraphy that includes a layer of thermal acoustic insulation material, a weatherproof membrane, and of course the finishing layer. Overall, any type of cladding materials are suitable to this type of panels, such as metal, ceramic, plaster, and composite. The main difference between the two panels is that in the main structure, the e-CLT is made of structural cross-laminated timber, while the e-panel is made of a wooden frame, which is lighter compared to the CLT. The panels are installed from the outside of the building. The installation of the panels takes place from the ground story of the building to the top one in this way. Firstly, the e-CLT are connected to the beams of the building through the friction dampers, while the e-panels are connected through traditional angle steel brackets. The panels are not connected each other in order to provide both tolerance for the installation, but also to ensure the relative movement in case of earthquake. After installing the panels of 2 consecutive stories, a gap is formed between these panels. To cover this gap, additional prefabricated panels are used. These panels are thermally insulated and were specifically designed to cover the connector of the panels, ensure easy inspection and maintenance of the dampers, reduce the thermal breach at the beams level, and also to ensure aesthetic uniformity on the building facade. Another technological issues concern the water tightness of the new wooden facade, since it is totally prefabricated and thus it is subject to the access of water through the joint between the panels. So to solve this problem, we have designed proper technical solution to be adopted. For instance, the vertical joint between near panels are protected on site by means of EPDM band, while the horizontal joint between panels applied on consecutive stories are protected by overlapping the weatherproof membranes of the panels. this on site. Each panel are also made of an air cavity that allow to dry future rainwater infiltration. The slide show the prototype of the panel that were tested to validate the performance of water tightness, air tightness, and mechanical resistance according to the European technical standard. These testing were carried out in Netherlands by the company Webbo, which is a partner of the e-Safe project. As regard the e-EXOS technology, as I told you before, this is a second seismic retrofit technology which is applied in combination with the e-panels and which consists of structural 3D steel chassis which are connected to the existing structure. At technological level, these chassis are prefabricated and are installed by means of dry technique in order to reduce implementation times. They also were designed to be highly customizable in their geometry in order to ensure high proper architectural integration in the facade of the building. Now, I will show you some possible applications of these retrofit technologies. Within the project, indeed, these technologies were applied in 3 pilot buildings, which are located in seismic countries with different climatic conditions. The first pilot is a residential building located in the city of Catania in southern Italy. Here are being applied the e-CLT and e-panels technologies that will give to the building the new architectural image that you see in this slide. The renovation works are currently in progress and are allowing us to demonstrate the effectiveness of the construction feasibility of this retrofit solution. The second pilot is a school building located in Romania, in the city of Timișoara, which is characterized by large windows on the facade. Here, only the project of the intervention was done, which involved the use of the e-panels in combination with the e-EXOS technology. As you can see in this slide, in this project, the steel chassis were designed to serve as a main architectural element, diversifying the geometry and color. Then the third pilot is a residential building in the city of Bucharest, also in Romania. Also here, the design of the intervention involved the use of the e-panels in combination with the e-EXOS. In this project, instead, the steel chassis were designed to support new balconies that instead are lacked in the current state of the building. Now I give the floor to my colleague Francesca Barbagallo, who will talk to you in detail about the structural performance of the e-CLT and e-EXOS technologies.
Okay, thank you, Carola. I'll share my screen. Okay, can you see it? Can you see my screen?
Yes, yes,
Okay.
Francesca.
Thank you. So, hello everyone. My name is Francesca Barbagallo, and I'm Assistant Professor of Structural Engineering at University of Catania. In this presentation, I'll show you the basic design guidelines and the structural effects of e-CLT and e-EXOS by applying these 2 technologies on the pilot buildings studied during the e-Safe project. As a first, let me introduce you the structure team. I'll talk on behalf of the structure team from University of Catania. It's composed by Professor Marino, Professor Bosco, me, Dr. Leni, and Dr. Ricciardello. My presentation will develop into 3 main parts. As a first, I'll provide you the guidelines to design seismic upgrading by e-CLT and e-EXOS. Then I'll present you the methodology that we follow to assess the structural performance of RC buildings. And in the end, I'll present you the seismic upgrading of the 3 pilot buildings in Catania, Timișoara, and Bucharest. So as a first, if we're supposed to have a case study building that needs to be upgraded by e-CLT, we need a preliminary design to determine the location, number, size of e-CLT panels and the connection between these and the RC members. As a first, you can suppose that e-CLT panels can be located in every span of every story, which is a quite straightforward solution. But actually, if you're able to perform a pushover analysis, which is quite common analysis in for an engineer, you might be able to determine if there are any concentration of damage. If so, you can adopt a more optimized configuration, which is a selective one, where you can put the e-CLT panel at the story where the drift demand is maximum, and also at the stories immediately above and below it. As for the number of e-CLT panels, again, you can suppose to put them in every span regardless of the size of windows. But actually, finite element analysis showed us that if you include windows with increasing sizes, actually the effect of e-CLT becomes more negligible. In fact, the presence of windows reduces large windows reduces the stiffness of the e-CLT panel. So we suggest to use e-CLT in blind spans, so without windows, or in spans with small windows. As for the size of e-CLT panels, actually they affect also the dissipative capacity of the system. To show this topic, I'll start from the basic reinforced concrete frame with measuring fields, and I'll show you a cyclic pushover analysis, which allows us to determine the cyclic response of this structure. So in terms of base shear and top displacement, the area enclosed in this cycle is the energy dissipated by the structure. If I repeat the same analysis, including a narrow or a large panel, you can obtain the same cyclic responses, but you can see that the area included in this plot is larger. However, if you have a slender e-CLT panel, the increase of dissipated energy is not that much. It's less than 30% compared to the original structure. While if you have a stocky panel, then the dissipated energy increases a lot. So there's also another point regarding the size of the panels, because if you have a narrow panel, so a slender panel, actually for a static equilibrium, you also have larger forces transmitted on the upper connection compared to those developed in the stocky e-CLT panel. So basically, these forces might be a problem for the beam, because they increase the shear and the bending moment in the RC beam, which is not necessarily able to sustain them. So basically, we suggest to adopt stocky panels, which have a larger dissipative capacity and can be connected directly or close to the beam to column joint. With regards to the connection between e-CLT and RC beams, they are composed by bolt and screw connection, which must be able to sustain shear forces or shear forces and tension forces due to gravity loads or gravity loads in seismic combination. And moving to the e-EXOS, again, if we start from a possible case study building to be upgraded, you need to locate the e-EXOS and determine number and size of the trusses. Keep in mind that e-EXOS works differently from e-CLT because it increases the structural response only in one direction, that is the one perpendicular to the sides, to the side where the e-EXOS are applied. In this case, the green e-EXOS work for seismic forces in the X direction. So as a first approach, you can suppose to locate e-EXOS along the sides parallel to both the direction in plans. And you don't have to worry about the location on the facade, because e-EXOS must not be necessarily located in correspondence of columns, because the connection works by means of the slab. Different configuration could be selected depending also on the features of the surrounding of the buildings and the surrounding buildings. So if you have building with a one-week direction, e-EXOS could be applied only for that seismic force, for example, the y direction. Or if you have confining buildings, you could apply e-EXOS along only one facade parallel to one of the in-plan axis. Or you can suppose to combine e-EXOS and also e-CLT systems. As for the size of e-EXOS, the steel truss must be designed to be stiff and strong enough to ensure a distribution of displacement demand of the building, which is as most possible as linear along the height, so to avoid concentration of damage. To this end, steel trusses must have high lateral stiffness. Their members must remain elastic during the seismic action, and in case the increase of energy dissipation capacity is not enough, it can be further increased by adding a damper, for example, buckling restraining braces. The plan dimension of the steel truss must be sized according to architectural constraints, of course, and the seismic performance of the original building. So when to use e-CLT or e-EXOS? Basically, you need to assess preliminary the structure performance of the existing building to determine the type of collapse mechanism, the ductility and shear capacity of members, and the presence of highly stiff members. Both interventions are very effective in case of good ductility of structure members, good shear capacity of members, and the absence of highly stiff members. e-CLT becomes less effective in case you have a low ductility or a low shear resistance of members or high stiff members which have untimely local collapse mechanisms. And e-EXOS becomes also less effective in case the original structure has already a quite global collapse mechanism. However, good performance can be achieved by combining e-CLT or e-EXOS with local strengthening interventions. So moving to the methodology to assess the structural performance of a building, we develop as a first a numerical model. Our structures will be analyzed by plane frame model in OpenSys with a beam with hinges element with fiber cross sections, including P delta effects and simulating the slab by rigid diaphragms. We included also the infill panels in our model. In case of the strengthened structures by e-CLT, the CLT panel was modeled by means of 5 equivalent elastic trusses, and friction dampers were simulated by zero-length elements with elastic plastic behavior. As in case the e-EXOS had to be modeled, the real 3D trusses were modeled into equivalent 2D trusses, where members of e-EXOS were supposed to be elastic, and they had an equivalent cross-section area that was modeled to take into account the difference between number, orientation, and the length of members between the 2D and the 3D model. The connection between truss and X is made by horizontal equal DOF, and in case of additional dampers, we put BRB model according to the nonlinear cyclic response by zone and Allasta material. So, given this numerical model, we perform nonlinear dynamic analysis of the bare frame and compare that to the response of the frames upgraded by e-CLT or e-EXOS. To do this, we use a set of accelerograms, at least 7 accelerograms, and increase the PGA up to 0.40 G. For both columns and beams, ductile and brittle mechanisms are checked in terms of chord rotation and shear forces, and we build the fragility curves aggregating the PGA corresponding to the achievement of the selected limit states, including only columns or only beams or only ductile failures or both ductile and fragile mechanisms. To just briefly let you understand how we evaluate the performance by fragility curve, this is a fragility curve obtained by considering only ductile mechanisms and provides a PGA capacity corresponding to 50% probability of exceedance equal to 0.36 G. However, if we include also ductile and fragile mechanisms, the fragility curves becomes the red one, which provides the lower fragility, the lower PGA capacity close to 0.21 G, which means that fragile mechanisms are responsible of the collapse. If we do the same, considering the fragility curves of only columns or only beams, we are able to understand which member, in this case the beams, are responsible of the collapse. So moving to the pilot buildings, this is the real pilot building in Catania, which is a residential building designed for gravity loads only with 5-story, with 5 stories. And from the in-situ survey and material tests, we were able to define the geometry. So the plan is basically characterized by beams arranged in the X direction, slabs, unidirectional slab in the Y direction, and cross-sections of columns that reduces along the height. So we developed a plane frame model for the weak direction, which is the Y direction, and we supposed to put CLT panels in external spans, which were one was a blind span and the other one had a very small window. And we supposed to use CLT panels with a 14 centimeter thickness and dampers with 26 kilonewton activation force. So we assessed as a first the response of the unstrengthened building, and we can note that the columns are the critical elements and they suffer from ductile failures. However, if we introduce the e-CLT, which is represented by the green plot, the e-CLT improves the response of the critical elements that are columns without changing the failure mode, which remains the ductile failures. And you can see that the PGA capacity increased by more than 35%. Moving to Team Shuara, this was a different structure because it was a school building, 3-story high with RC frame structure, and it was located in Team Shuara. In this case, we adopted the e-EXOS because there were too many and too large windows. So basically, there was no space for e-CLT. And the in-situ survey allowed the determination of geometrical and mechanical features. The structure was designed for gravity loads only, presented a quite poor quality of concrete and steel, but especially a very low amount of stirrups in beams, and especially in the internal columns of the first story. So we developed this solution, 12 e-EXOS in the Y direction and 2 e-EXOS in the X direction. And this is a possible representation of the architectural features. In the unstrengthened building, the Y direction said that the beams have a larger probability of exceeding the significant damage limit state due to brittle failures. And the same behavior was recorded also in the X direction, but with larger fragility. So indeed, you can see that the PGA capacity in the X direction was lower than 0.1 G. However, the target required by the code was 0.20 G. We introduced the e-EXOS, and actually the improvement was appreciable in the Y direction, but however, PGA capacity was lower than 0.20 G in both directions. This was due to the fact that there were untimely local failure due to shear failures in some columns, in some beams and one column of the first story. So we had to reinforce these members locally, and adding this local intervention, these local interventions to the e-EXOS allowed to increase the PGA capacity significantly and to reach and overcome the value required by the code. In the end, this is the residential building in Bucharest, which is a residential building with 5-story high. But the structure actually was not the one that we expected at the beginning, because it was not an RC frame structure, but it was a masonry panels confined by lightly RC members, and it was located in Bucharest, which has a quite high seismicity area. The in-situ survey determined the geometrical and mechanical features of the building again, and put in light that the structure was designed for gravity loads only, with a very poor quality of material of both reinforcing concrete members and masonry panels. So we suppose this type of interventions by e-EXOS, 10 e-EXOS in the transverse direction and 8 along the longitudinal direction. And in this case, since the structure was not made by reinforcing concrete members, we had to change a little bit our approach, because we assumed a capacity of the masonry resisting system equal to a low, medium, and a high drift capacity. And we compared the seismic demand, which was the maximum story drift angle determined by nonlinear dynamic analysis. The comparison between seismic demand and capacity provided the PGA corresponding to the attainment of the considered limit state and allowed to build the fragility curves, as I already shown in the cases before. So starting from the 0.5% drift capacity, we can see that the original structure has a very low PGA capacity in the y direction lower than 0.1 G. However, if we introduce the e-EXOS, especially in the y direction, the PGA capacity increases by about 70%. If we move to the 1% drift capacity, the e-EXOS becomes even more effective. And if we go to the 2% drift capacity, the e-EXOS is able to increase in the y direction the PGA capacity more than 130%. Why these performances were obtained? We had a look at the distribution of story drift demand along the height, corresponding to the 2% drift capacity of the original building. So in this plot, you can see by the red lines the drift demand along the height of the original building. And you can see that in both directions, but especially in the X direction, there's a concentration of damage at one story. When we put the e-EXOS, actually the drift demands that are represented by the green lines becomes much lower, and the distribution along the height becomes much more uniform. So this was the effect of the e-EXOS, avoiding the soft story collapse mechanisms and mitigating the story drift demand. So in conclusion, two seismic upgrading approaches were presented and also their very basic guidelines to design interventions. The three pilot buildings that were presented showed the effectiveness of e-CLT and the e-EXOS because both of them were able to reduce the demand and increase the PGA capacity of their strengthened buildings. In some cases, the effect of retrofit intervention can be compromised by brittle failure or local failure, but the combination with local strengthening of members can be very effective for the retrofit intervention overall. So that was my presentation. Thank you for your kind attention.
Thank you. Thank you very much to all of our speakers. And now I would like to open the Q&A session. So let's see if there is some question. Can you see my screen? Yeah. So the first question is maybe for Carola Tardo. How can the panels be customized?
Yes, Veronica. So, how can the panel be customized? So the panel can be customized in terms of structural and thermal performance according to, of course, the boundary conditions of the building, but also in terms of aesthetic appearance. According to the desire of the users and the owners. For instance, the size of the structural component, such as the e-CLT and the friction damper, of course, are designed based on the level of seismic improvement to be achieved. Instead, the condition of instead the type of thickness and the type and the thickness of insulation material can be designed according to the boundary climatic condition of the building. As regard the panel was conceived to integrate, of course, a new window combined with also new external sun shading system to reduce the indoor overheating, such as Venetian blind or rolled shutters. So, of course, you can also decide to plan to keep the existing windows. As regards the cladding layer, the panels, as I told before, the panels are suitable to any type of cladding material, such as fiber cement, wood, metal, ceramic. Based on this type of cladding material, it is possible to decide to install the cladding layer on site. Or to integrate this cladding layer into the panels of site. So this has all the technological aspect that allow us to make customizable these panels.
Thank you very much. So now I read another question. How can the adequate level of friction can be verified in the system? Maybe Professor Tomasi can answer this one.
Yes, exactly. This was one of the first question we have in this in the design of the system, because of course the system relies on friction, and that's why we have introduced this cap plate to reach like to have a higher area that is involved in friction. And in the test phase, we tested different level of pretension in the system, and that we found that was necessary to have around 30 kilonewton per bolt for this for the target capacity that we wanted in the system. There is of course a problem of maintenance of this level in the structure. So it's important to have because of course we monitor during the test also the possibility to the variation of force in the pretension bolt. And this is possible. The system is conceived as it is possible to intervene and repristinate the level of friction after some years. That was specifically one of the demand of the design of also technological design of the dissipative connection.
Thank you very much. And I see another question. Is residual drift significant for the e-CLT solution when friction behavior is activated? I don't know who wants to take this one.
Yeah, I can answer to this one.
Mm-hmm.
Let's say the residual drift is an issue. Every time you have a system based on friction, when the force disappears, the system can be left, let's say, partially out of the original position. But if you look at the cycles I show you at the beginning, the amount of residual displacement was not so important until you reach really large drift. When you are talking about 2-3% of drift, the reinforced concrete system is mainly damaged, is mostly damaged. So the problem of coming back to the original position is no more an issue. There are other issues. But at that time, and in that way, the wooden system, the e-CLT panels and the dampers can also sustain the damaged reinforced concrete elements. So there is an issue about the residual deformation left in the system after the fading of the earthquake. On this, we are still working, but as Professor Tomasi told you before, we are testing the system also on shaking tables to understand the dynamic behavior of the system, of the dampers, and to date, the residual displacement, the residual drifts were not so important, even when imposing large interstory drift.
Thank you very much. The last question that was sent is why the slender e-CLT panel has a lower dissipative capacity?
Okay, maybe I can answer this
Yeah,
question.
please.
It's basically it's related to the in-plane stiffness. If you have a slender panel, the in-plane stiffness is lower than a stocky panel. So what happens is the following one. The drift of the RC structure, ideally it should turn 100% to displacement of the damper. So if you have an infinite stiffness of the CLT panel, 100% of the sorry drift turns into displacement of the damper, so turns into increase of dissipative capacity. If the panel has limited stiffness, then part of this interstory drift is lost as CLT deformation. So if you have a slender panel, a larger part of the drift demand turns into CLT deformation, and a minor part turns into damper displacement. If you have instead a stocky panel, it's more stiff, and only a very small amount of the drift demand turns into deformation of the CLT panel, while the majority becomes displacement of the damper, which dissipates more.
Thank you very much. I'm seeing more questions, so I will ask you to answer quickly because we are running out of time. So next question is, which insulation material do you use in the panel system? I don't know who wanna speak about it.
Can I as well?
Yeah.
Can I as well? Yes, of course.
Please.
We can use all the type of insulation material on the building market. For instance, in the pilot building in Catania, we and also during the prototypation of the panels, we use wooden fiber insulation material that we protect with a cement-based board to, of course, ensure fire protection of the panel. But overall, we can show all the type of insulation material, of course.
Thank you, Carola. And the last question, the e-CLT thickness of 14 centimeter is required for strength criteria or for other technological issues?
Maybe it is referred to the thickness that we adopted in the Catania pilot building. Actually, we tried with different thickness, and at the end we obtained satisfying performance by using 14 centimeter. So yeah, it's basically basically related to satisfy the significant damage and the near collapse limit state. So strength, let's say strength criteria, and what it was not given by technological issues, but it was necessary to satisfy the target limit states. With a lower thickness, we couldn't satisfy the target limit states.
Thank you very much. And yeah, we reached the end of our webinar. So thank you very much to all the speakers. I strongly encourage all of you to follow e-Safe on our channels. And yeah, you will find this webinar and the news about the next webinars on our website. So thank you very much and see you next time.